Thank you. Thank you very much for giving me the opportunity to talk in this beautiful place. So I will discuss assisting sampling of physical systems with generative models, and maybe just to take the stage of, take the opportunity of setting the stage of how statistical mechanics and machine learning are interacting for a few decades now, and in particular here as well. I would advocate that they are reciprocally bringing some insights into complex systems, either using neural network or taking neural network as objects in particular. And as I said, there's definitely all the demonstration of this taking place in this Cargèse edition, with the first chapter that opened on using physics of disordered systems to study neural networks. And we had some demonstration of this in the different talks, and we will have more throughout the week. A second chapter that opened on using inspiration from statistical mechanics to define so-called generative models. So I will come back to one definition of generative models, but we have already heard from them about them by the talk of Eric and Mark on diffusion models, and I'm sure we'll hear even more at the end of the week with the Boltzmann machines that historically were maybe the first generative models and inspired from spin systems in the talk of Aurelia and Bea. And this talk will be about a third chapter, I would say the last one that has opened, and that is taking advantage of the amazing progress of machine learning and the amazing ability of interpolation of neural networks that Eric and Mark already mentioned, to try to have some insight into many-body systems. And so again, this is where we're gonna be in this talk. So this talk, more precisely, will be about sampling. So I don't really need to justify sampling to this audience, right? We have a Gibbs-Boltzmann distribution. We want to understand the statistics that are constrained by this Gibbs-Boltzmann distribution on a given system. But maybe what I should insist on is that I have in mind really this setting where I want to study a specific system, and I don't want to choose the system such that it's amenable to, some replica calculation or some specific type of algorithms. I want to have algorithms that are a bit agnostic, of course not entirely, but to some extent to the type of system, and try to go after them. And as you know, to retrieve the macroscopic statistics given density, we are going to need to do some Monte Carlo approximations to estimate any type of observable expectation. And if I will take the stupidest example I can think of to try to illustrate throughout the talk the algorithms I'm going to be mentioning, and this very simple system is a particle that would be lying in a two-dimensional surface with two wells. So generating the following distribution with one well that is maybe deeper than the other, and so that is twice as likely as the other, right? So why do we need sampling? We need sampling to be able, for example, from realizations, to realize that one of the two wells is twice as likely as the other one. Okay, so far I've said nothing really complicated. But of course, again, this is something that I don't think I need to justify to this audience. Sampling itself can be very challenging. And it's specifically the case for metastable system, or in the language of probability, multimodal distribution. That is, when we have mass, we have a region in the state space we are interested in that has very low mass that separates region of interest with high probability mass. And here I would like to state maybe more directly to this audience that this problem is hard, even if you don't have exponentially many states everywhere in your landscape. Even if you have just a couple of states, sampling from metastable distribution is hard. So maybe that's something that is very clear to many of you, but I also think that it's always good to have some intuition to remind ourselves of what makes sampling hard. And for this, I can think of two 101 sampling algorithms that you can study, from which you can get really this intuition of where the complexity of the task comes from. And so if I keep my very simple system, and I consider a first wide class of algorithm, that is algorithms that are going to shoot everywhere in space and then either accept, reject, or re-weight. It could go something like this. I take a simple distribution I master very well. It's a unimodal Gaussian. I put a bunch of realization on my state space, and then I can reweight them, so in this importance sampling algorithm, by simply considering what's the density of the targets where I lay my points compared to what was the probability of generating those points. And so you see that you can give more importance to the points that were indeed where there is an high mass. So I gave them a radius that is accordingly large. And using those weights, you can ponderate sums and show that those ponderated sums are asymptotically unbiased estimators of the expectations that you care about. However, what's the problem? Why am I saying that this is hard if it looks like I've solved the problem? Any guess? So I had all those points. Remaining after I did my reweighting is really a fraction of them, right? So I wasted a lot of computations, shooting everywhere in space, and in the end, ending up a lot of time in places where I really don't care about what's happening. It has really no weight in my target distribution. And therefore, and I've wasted a lot of computation, and on top, it means that I have only a few points that are really the one I'm using to make my estimation in the end, and therefore, I'm going to have a high variance in my estimators, especially because this phenomenon is just going to become more and more problematic as the dimension increases, and so the fraction of the interesting mass is going to become smaller and smaller among all the state space. So that's the difficulty in using those shoot everywhere in space algorithm and then accept, reject, or reweight. But of course, in higher dimensions, something that is considered state-of-the-art is more to look at Markov chain Monte Carlo algorithms. And typically, what they do is that they rely on local updates with an update rule that is going to make the distribution of realization flow towards a stationary distribution that is my distribution of interest. And so here, I have a little animation of two chains of one type of Markov chain. And if I run it on my stupid example, I obtain the following outcomes. So why cannot I just use all the realizations that come out of this Markov chain to make a reliable estimate? Correlation time, that's true, but here it's how it drastically shows that correlation time is a problem, if you want. It doesn't jump between the different states, and so in particular, my relative estimation of the weights of the two worlds is purely inherited from my initialization. And maybe I said never, but it's not never, it will eventually jump, but not within the time that I'm willing to spend looking at this simulation run, or even leave my computer running this simulation. So in the end, the outputs for those metastable distribution is typically bias if you use those local update Markov chain Monte Carlo. So on one hand, you have something that could explore the different worlds, but that doesn't handle well the increasing dimension. And on the other side, you have something that scales better with dimension, but that doesn't handle well multimodality. So of course, there is a whole literature that is trying to tackle this problem, and such for decades. Some key ideas are to use different temperatures and coupling different temperatures of a system to promote some transitions between states. But tempering is also difficult to implement because you need to choose the number of temperatures you need. You need to make sure that you have mixed in the end. I mean, it's not trivial to tune, and ends up being costly when you have all those temperatures to run in parallel. And so this is why this is not what I want to talk about today, of course, but I want to talk about another direction of research which would rely on the progress of generative modeling to try to tackle this problem. So I'm not presenting to you anymore generative models. There has been a lot of groundbreaking progress in this field for generating images, for generating sounds, for generating text, so on and so forth. Generative models come in different shape, but the one I would like you to have in mind in order to follow is one that I'm expecting a lot are familiar with, but they are called deep latent generative models, and the way they work is by having a base distribution that is a very simple distribution, for example, a Gaussian multivariate distribution. that your computer can generate independent realizations of very quickly. And then having a transformation that is parameterized, such that the output is considered as the transformation of the simple random variable by the parameterized transformation. And so, of course, here you have neural networks under the hood. And if you do your training according to the state of the art today, say on a dataset of images, you could transform an image of pixels completely random into a nice-looking image of a dog, as we have already seen some realizations by Eric yesterday. And of course, you have to think of this as a generative model in the sense that each time you draw a new random realization at the input, you get a new image at the output. So for example, if you trained on images of dog, you will get a new image of a dog. And then effectively, this construction defines an effective distribution that is parameterized by a set of parameters that corresponds to all the parameters in the neural network in the transformation here. So we see this, we have a very, should I say, expressive class of distribution, rho theta of x, that can fit distribution that looks like as complicated as images of dogs or real-world images. And once we have trained them, it's very easy to obtain independent realizations from them. So it really sparks the idea of whether, the question, whether or not we can use them in order to speed up sampling of physical system we may want to study. So as soon as you formulate this idea, you're going to see that you have two big questions that are going to arise. The first one is, can we guarantee the outputs of the generative models that we are going to use in scientific context? Because we know that they are very impressive, but we also know that they are prone to errors that are hard to control and hard to predict. So for example, I took from this paper about images this example where you have a very nice mountain lake image. The only problem is that the reflection of the mountain on the lake is inconsistent with the mountain. So you see there is no physics constraint of having something that respects some rules that they are embedded in. So that's of course of concern if we want to use generative models to do scientific computing and to infer some properties, some physical properties about systems from them. And the second question is, can we train without extensive data? Because of course all those very impressive progress, and as we've heard again yesterday and today, they rely on having access to very large data sets that are going to give us the input to do the training of the transformation. Here, this is not at all the context I'm at. Instead of having my generative modeling task where I have a very large data set, my input is simply a distribution that I would like to be able to sample from, and so I don't have those realizations to start with. So how do we go around this problem? Well, for the first part for the first question, actually, a set of pioneering works have quickly answered this question, in a sense, by resorting to a specific type of generative models that are called normalizing flows. So normalizing flows are working exactly like what I showed you before, except that they are going to impose that the transformation T theta is a diffeomorphism, such that you can use a change of variable formula to write down explicitly the likelihood of your model, that is this density rho theta of x. And the fact that you can write the density rho theta of x makes it that you are able to use your normalizing flow within a Monte Carlo strategy that will have all the guarantees of convergence towards a target distribution that we usually have in Markov chain Monte Carlo or other sampling approaches. And so if I take again my very stupid example, if I had been able to train a normalizing flow such that I would approximate my target distribution with this gray level approximate density, for example, I could replay my importance sampling algorithm where I propose with the flow, but this time much more focused on the high density region, and I reweight, losing a lot less computations and having a much lower variance thanks to the targeted learning of the generative model that again could fit something much more complicated than this simple bimodal distribution. I could also use, once I have this normalizing flow trained, Metropolis Hastings algorithm, which is a Monte Carlo Markov chain algorithm, where I need to know the density of my proposal, and where here the proposal will be simply the normalizing flow density, meaning that non-locally you will propose in any of the two worlds, completely independently at each step, and so your correlation time will be very small, and you will be able to mix in between the different samples, in the different worlds, states. So if you want, this answers to the question of the quality of the output, because you shouldn't think of the approximate generative model that is never perfect. I mean, deep learning is never providing you something that is controlled, but you can incorporate it into Monte Carlo strategies that here, yes, you have a control over, and therefore it really answers to this question. However, with the premises that indeed I had a method to train my normalizing flow, such as I had a good initial guess of where were the high mass regions of my target distribution. So that's my second question. Can I train without extensive data? Well, there's different ways you could imagine training without extensive data. For time concerns, I've chosen to not describe everything that has been proposed, but simply one of them, and the one that we worked on with Eric van den Eyden and Grant Roscoff, that has simply the idea of solving this problem iteratively, and so learning a non-local proposal, so in the shape of a normalizing flow, while sampling. So what do I mean? I mean that we're going to loop over 3 steps. The first step is simply to run your favorite local Monte Carlo algorithm that you know is giving you some biased information about the global repartition of the mass, but however is still telling you something about how things look locally in your landscape. Once you have run this algorithm, you can use the outputted realizations as data to seed the training of a generative model. This generative model, again, doesn't have any information about how mass is globally represented, what is the relative weights of the two worlds. However, once you have it, you can run a non-local method by using the flow itself as a proposal in a Monte Carlo Markov chain, and therefore retrieve from the realization of this second Markov chain this global information about the global reweighting. And so, of course, in practice, we don't do this 1, 2, 3, but we loop over all a small number of steps of each one of those iterative algorithms. And so it yields a video a bit like this, where we're going to have the flow that is learning to concentrate on the high mass regions in the background, while the chains are going to converge to the target distribution, mixing very well between the two worlds. So this solves, if you want, the two problems of guaranteeing the quality of the output and training without extensive data, because all that I needed to have was one worker that started in one well and one worker that's starting in the other well as the seeding information for the algorithm. There is no free lunch, however, because if I hadn't done that, and if I had only initialized a worker in one of the wells, then there is no reason that the algorithm would have discovered a new place that was far away from the one from the basin of abstraction of where the workers were originally initialized. And so there is no claim that this algorithm is able to discover mode, but provided that you have this minimal set of information, you are able to construct a fast mixing Markov chain in between the two wells. Okay? So, since those initial works, there has been proofs of concept of using those generative models for sampling physical system. One very notable paper that was one of the pioneering works is the so-called Boltzmann generator paper that was focusing on molecular systems. We've had some demonstration of how you can also use this technology of normalizing flows, so invertible generative models, to compute free energies. So, for example, here, binding free energies. There is also some works about looking at liquid systems and example liquid systems. We have something about more crystalline system. We have even Ludovic and Giulio that realized the feat of using these to Glassy System, close to Glassy System. and showing that there is some hope in using these technologies even in such highly complicated systems. But there are also other types of physical systems that people are trying to apply those methods on. So, for example, latticed field systems for quantum chromodynamics are also having a large push of at least one group in MIT, led by Fiala Shanahan, on trying to really make progress on those very complicated sampling problems. There is also, if you're interested, a nice review opinion paper that came out on those topics. So to fix the ideas, I chose to tell you about one concrete example of use of those methods, one that I was involved in. And the system I was interested in with my colleagues Olga Lopez Acevedo, Pilar Cosio, and our student Ana Molina Taborda was the system of isomers of silver atoms. So at room temperature, there are two credibly stable isomers of those 6 silver atoms. And of course, if you run a molecular dynamics simulation, you're not going to see, well, not of course, but it turns out that if you run a molecular dynamics simulation, you're going to see one of these two isomers oscillating, but it's going to happen on a too large time scale, again, that you transition from one to the next. And so you cannot really understand what's the relative proportion of isomers only from this type of simulations. So we played this game of implementing this normalizing flow-based sampling algorithm on this system. So again, having this loop of training a model, propagating an MCMC that uses proposals from the model, and then using the data that is produced by the MCMC to update the dataset and retrain the model, and so on and so forth. And doing this, we were able to obtain some Markov chains that are going to sample indeed the two different wells, so realizing that one of the two isomers is much more likely than the other one. And we could check, for example, have one diagnostic of convergence of the Markov chain that was pretty encouraging. So it's the potential scale reduction metric, so also called R hat, that basically is going to compare what's the variance within a chain and across chains. And in an ideal world, it will be equal to 1 once you have converged, and it's always larger than 1. And so we get somewhere not too far. So that was one result of this study, but we also, since I guess the talk was initially marketed as machine learning for scientific computing, I also added this second part of the study that was to speed up further this Markov chain by also introducing a supervised learned potential this time to save cost in the simulation. So here, those nanoclusters, when you simulate them, you need to resort to density functional theory to predict energies and forces. And this is something that is extremely costly. So it's becoming more and more common in the molecular dynamics, the ab initio molecular dynamics community to use machine learning potentials to regress the DFT force field on the fly. So really paying sometimes the price of querying this density functional theory to get a training point of what is the value of the energy and what is the value of the forces at this specific location in the state space. And sometimes trusting that you have machine learning model that has been trained accurately enough to predict by itself the forces and the energies. And so we played this game of training two models instead of one. So having the normalizing flow for making proposals that are non-local and the machine learning potential that, again, was going to predict the energies that we need to compute when we do the accept-reject step of the MCMC. And so, doing so, we obtained chains that were looking alike in this projected space, and that we could check was indeed going to to speed up the convergence of an MCMC chain, given that we also factor in, of course, the additional cost of training an extra model in the simulation. So, an example of how, again, machine learning can help, and in particular, how those normalizing flows can really be applied to concrete physical systems. So, with this example being presented, I should also confess that with all those initial study and proof of concept, we are also realizing what's the limit of this approach. And the limit of those enhanced sampling approach with generative models is when it's becoming difficult to ensure that the generative model we are training is close enough to the target distribution we are interested in. And so this can happen for different reasons. One reason is the landscape is becoming too complicated, or merely the dimension of the problem you are interested in is becoming too large. So, okay, what can we do about this? So I think probably unsurprisingly, or probably coming in as a relief, the answer is that we need to combine learning with physics knowledge, and we cannot leave it all to the learning. So let me give you two examples of how we can combine learning and physics knowledge in this context. So the first example is a relatively simple example where we had a way of handling small scales directly with tailor-based, system-tailored base measure. So here we were interested in this example field system, that is the 5-4 model, right? Where the action that is going to enter into the distribution we care about is going to have a coupling term and a local potential, such that here we were placing ourselves in a 1D grid. Typical realizations will look like this. So we would have the field phi as a function of a position that will go from 0 to 0, and either going through +1 or through -1. So here you have 4 typical realizations, and so you see that it's a bimodal distribution with these two types of configurations. So what we did was to think of a base measure that will actually retain from the actions all the quadratic terms. So if you want to have not an isotropic Gaussian measure at the base measure, but have something that is colored, and that is colored in the sense that it reproduces the local fluctuations in the target action. And so doing this, we went from typical realization of the base measure that will be this just purely random noise into something where there were correlations between neighboring sites that were consistent with the target distribution. And making this simple change was really key to having a sampling algorithm that across this iterative loop of generating the data and learning from it would go from 0 acceptance in the Markov chain because the proposal of the generative model are nonsense at the beginning to something that is actually going up to, for example, 60% acceptance. And here it's for a system that was discretized with 100 sites, so it's really a 100-dimensional system that we are sampling from. And so you go from a base distribution that is like this, and effectively we initialize the transformation by the identity. So this is your, if you want, initial normalizing flow, and at the end of learning, it generates trajectories like this one, so 60% of which you typically accept into a Markov chain to generate those typical configurations. And so here it was one example of how we can think about the physics to try to ease the learning by putting in directly the small scales. Now, a second example I want to mention is recent work I've been involved in with different collaborators I will just mention, where the idea is to really exploit the underlying low-dimensional structure of the problem, because oftentimes it does exist. So the idea is that sometimes the measure you are interested in can decompose into hard and easy degrees of freedom. So here, what do I mean by this? So I took, again, a very simple example. I have a z variable, and I have a x perp variable. So actually, I would think of this one being potentially high-dimensional. And my distribution over this joint law of z and x perp can be decomposed into a marginal on z and then a conditional of x perp knowing z. Here it turns out that I have set up the problem such as that x perp knowing z is actually a simple distribution. So here, when I mean x perp knowing z, it means that instead of normalizing the distribution over the whole picture, what I did was to normalize row-wise the picture such that I do have a distribution for each value of z that is perfectly normalized. So here, if I have this other visualization of what are the perpendicular degrees of freedom given the z variable, we can see that all of them are easy to sample from. They are very simple. And remains only the marginal density that is describing all the metastability of the system. That would be this z variable here. And that would look, for example, the marginal like this. Okay. So typically, I can think of many problems where actually I can find a low-dimensional distribution that will be multimodal but low-dimensional again, and such that if I condition my target measure on this low-dimensional variable, I can have a high-dimensional but easy distribution to sample with. So this is something that is, of course, very common, and in the literature of enhanced sampling, widely exploited. Here we can think in our framework of using normalizing flows and machine learning in general, that what we need in the end is to focus the efforts where the metastability is. So in this low dimensional space, if you want, in this z variable, yes. And then we can resort to simpler strategy to get to sampling this conditional distribution that is much simpler. So the issue is that the marginal distribution, this rho star of z, is indeed a marginal distribution over all the remaining degrees of freedom. That is, again, typically something that is high dimensional. And so we don't have access to this marginal distribution rho star of z. So if we don't have access to it, it means that we cannot write directly a sampling algorithm for it. And therefore, we need to be a bit smarter in the way we attack the problem. And so the way we did it was to resort to non-equilibrium path proposals and accept-reject criterions that were previously exploited in different papers and maybe sometimes in slightly less general framework, but that were definitely already there, sometimes with the name of super detailed balance or the residence weight algorithm, or again the non-equilibrium candidate Monte Carlo. And that goes as follows. So I have my two-dimensional space of usually higher dimensional, but for the picture two-dimensional, where I have my variable that is capturing the metastability, and I have the perpendicular degrees of freedom that are easy to sample from, given that I condition on this first variable z. And what I do is that I start from a given point in my state space, and I propose to jump non-locally. So here I imagine that I've learned my normalizing flow already, so I can jump to a far away but sensical position that would be this one. And once I have this new proposal that I don't know whether to accept or reject again because I don't know the marginal distribution on z, I can construct an entire path for the entire state space, so both for z and x perpendicular. And so how do I do this? Well, I do this, oops. Interesting. Okay. I do this the following way. So I start by discretizing the path that leads me from my initial z0 to my z tilde, that is the proposal new location of this variable that is capturing the non-metastability. And maybe what I forgot to say is that we typically call it a collective variable, so CV, this z variable. And so I discretize a path that goes from z0 to z tilde. And for example, I can just do a very simple linear interpolation where I start at z0 and then I just increment for a given total number of steps, capital N, the steps to create this schedule. Once I have this schedule, what I can do is drag the rest of the system according to this progressing schedule of the collective variable. And so I can choose a Markov kernel that are going in spirit to relax the perpendicular degrees of freedom given an updated value of the collective variable and the previous position. So just on the sketch, I'm here, I update the value of z, I equilibrate with a Markov kernel that can be, for example, a Langevin inspired kernel, and I do so on and so forth to create a full path that will eventually lead to a proposal new location that is so far away from the initial point, and that is based on my non-local proposal for the rest of the degrees of freedom. Okay, So once I have this, the question is, do I accept or do I reject this proposal? How am I sure that I can construct an algorithm that would be reversible with respect to the target distribution? Well, again, I told you that this is things that have been already written and that bear some, maybe I say that, let me just maybe slow down a second. So so what do? You consider the past proposal probability density. So what was the probability density of generating this move? I first generated with my non-local kernel a new location for the collective variable, and then I took successive steps of the Markov kernel. So here I took a capital K that is the same for all the steps, but it could depend on the step. You just need to be careful in your evaluation of this. And now, in order to be able to do the accept-reject, you will need to have a probability of a backward move. And here you actually have some freedom into choosing which backward move you consider, but you have to stick to choosing one way of going backward. And one that is very sensical is to take the same path backward. So it means that now, let's imagine that now I had, from this location, proposed to go to z0, so this value of the collective variable with my normalizing flow. And then I had took the same type of kernel to go backward, so this time going reverse in time. So given that I fixed for myself this backward path and the probability that my scheme would have generated this backward path, I can write an acceptance criteria that is a sufficient condition for enforcing detailed balance with respect to the target distribution. So it's not at all necessary, it's even, if you want, it's stricter than detailed balance, but it's sufficient for detailed balance. So if I use this acceptance criteria that looks like a Metropolis Hastings, the mean between 1 and the ratio of the density at the target over the ratio of the density at the previous location times the probability of the reverse move over the probability of proposing this move, then I'm guaranteed that I'm sampling in the target distribution. I'm sampling in the long run from the target distribution. Yes. 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 There is no marginalization. That's the point, right? So you can compute the product of all those kernels. So that's one way of presenting it. Then you can, if the kernels are reversible with respect to the time-moving potential, then it becomes a work. And there is a link with Jarzynski equality. And actually, so maybe I also forgot to mention that this work is a recent work that actually has two folds. So one with my student Christophe Schönler, Tony Lelièvre, and Gabriel Stoltz, and that explores a bit all of the mathematical aspects of those algorithms and all the variations you are allowed. And one with Samuel Tamagnone and Alessandro Laio, where we implement it on a toy system that I show you just right after. Are you good? Okay. Okay, so in essence, what I managed to do is to have a non-local proposal that is on a lower dimensional space where I can hope to learn a machine learning algorithm that is going to handle the multimodality. And on the other hand, have an acceptance criteria that is based on the knowledge simply of the target distribution, which is exactly what I have access to. And this was at the price of generating a full trajectory for the entire system, so from my previous location to the one that I'm eventually proposing. Okay, so now what I haven't said is how do you learn the coarse-grained proposal, so the one on the CV space. Well, you do it adaptively, just like I had mentioned before, when I was not yet concerned with the dimensionality of the problem. And so, to maybe illustrate it, I will directly take this test system on which we have tested this algorithm with, again, Alessandro Laio and Samuel Tamagnone. And it's a system that is a very simple polymer with 9 beads that is in a solvent of Lennard-Jones particles. And it has two stabilized states, one that is open and one that is closed. So what we do is that we have, one that is open and one that is closed. Maybe let me do it this way. So what we do is that we add a double well potential that is on the distance of the end-to-end distance of the polymer, such that we can vary the energy barrier that we have between the two states simply by tweaking this potential. And we take as a collective variable, instead of having all the polymer plus all the solvent, simply the polymer. So it's a 6-dimensional CV space. As the bonds have fixed lengths, that's what we end up with. And we implement the algorithm where we are going to learn adaptively, again, the proposal on the CV space, so here, simply on the polymer. So how does it go? It goes like doing some MD steps on the entire system, some local steps, then some non-local steered updates that I was just showing you at the previous slides, and again, that consist in proposing with a normalizing flow, then deciding for a schedule to go to the previous state of the collective variable that was maybe very open this way, to the newly proposed version, so do this steering, generate the path for the full system, and then doing the metropolis accept reject in order to be able to jump from one state to the other, and then collect the data in order to train the proposal in this CV space, simply because when we observe the full Markov chain, we can of course simply take the marginal distribution, the marginal realization of the polymer that is taking that is our collective variable, in order to learn the generative model on the data that is generated this way. So we do this, and what we observe is that indeed we are able, when we benchmark against, for example, long molecular dynamics with the small energy, the small energy barrier in the double well potential, that we are going to have an algorithm in orange that matches perfectly a projected free energy profile with respect to the end-to-end distance. So with the two minima of the closed and the open that are here and here, I forgot to put the arrow perfectly, even though, again, the normalizing flow is imperfect. If we look at the distribution of the projected realization of the normalizing flow, it's not going to be exactly matching the target, but we can correct it with this scheme. So here we get to around, I don't know why, we get to around 50% acceptance of non-local move. So again, it's a system that has maybe around 200 Lennard-Jones particles with the polymer inside. So it's really a non-trivial task to jump from one configuration to the next. And so again, we can see that we did something correct in the 1D picture, but actually one advantage of the method is also that you are regressing, in a sense, the potential, the marginalized potential at the level of the collective variable with your normalizing flow. And so it's actually a 6-dimensional space quantity. And so you can try to look at a bit higher dimensional projections. Of course, you can look at different 2-dimensional projections. So that's just other 2-dimensional projections that are looking pretty convincing as well. And most importantly, the cost of state jump actually depends weakly on the height of the energy barrier between the two, because when we look at the other version of the example where we dramatically increase the size of the energy barrier, then it's very hard to observe what's going on at the barrier. So in particular, we need to bias the molecular dynamic simulation to provide us with a reference, but then we can debias it and get this nice picture where the Monte Carlo simulation based on the collective variable move proposed by the normalizing flow are indeed matching perfectly around the basins, the statistics. So something that I'm quite excited about, and of course that will need further demonstrations, but that marries this idea of tackling with learning the multimodality, but in a reduced space, and on the other hand, rely on the physics, and here we are indeed using Langevin kernels to relax the rest of the degrees of freedom along the path. So, right before I conclude, there is another direction of research that's, for the interest of time, I'm not going to get into, but it's a direction of research that uses inspiration from generative models to create samplers that are based on denoising. So as we discussed yesterday and this morning, we can try to start from something that is very simple and then progressively denoise it to the target distribution, again, paying always very much attention whether or not we get the global statistics. So this is something else we are starting to investigate, in particular with my student Louis Greniot and the student of Alain-Olivier Rodurmus, Maxence Noble. And with this, I will just add a couple, conclude on a few thoughts on the perspectives of these approaches. I think that, as I think Eric also mentioned, there is the progress in generative modeling is seems to suggest that really there is a way of making use of them to analyze and to simulate complex systems in physics. In terms of sampling, I would say that the methods I presented are actually seems to be off the shelf now if you are in a moderate dimensional setting, and this could be not because you are interested in sampling a glass, but because you are interested in sampling a Bayesian posterior that is a few parameters large, but for which you expect that there will be a multimodality. So the point is also that reaching the level of training accuracy that is required for complicated systems makes it that you cannot just go and try to learn everything from scratch, but that you really have to think of how you can rely on the physics and what you can handle from the physics point of view, and whether or not the machine learning approach can help you take care of the rest. And with this, I thank you very much for your attention. Yeah.